Hello everyone, my name is Ricardo Spina and this is my video lab report for Lab 4 Circuits and Capacitors. In this lab, we began by creating a direct current circuit in the circuit construction kit. By varying the components of the circuit, we obtained ammeter readings that helped us learn about the impact of different instruments. We then made a resistor capacitor circuit in the circuit construction kit and measured the time it took for the capacitor to charge and discharge with different levels of resistance to obtain the capacitor's time dependence. Some of the fundamental physical principles important to this lab were current conservation and understanding that current is constant throughout a circuit, energy conservation for understanding the impact of different components of the circuit, the node rule for understanding that current in and current out are equivalent, and Ohm's law for voltage and resistance calculations. Some of the key results of this lab were that we gained greater insight into the effects of different circuit instruments and computed an RC value of 6.689 seconds from our model compared to a theoretically calculated one of 6 seconds. To set up the first direct current circuit, I began by adding two 1.5 volt batteries, two ammeters, and two resistors, one with a resistance of 47 ohms and the other 100. The ammeters read a current of 0.02 amperes for the circuit, and when reversed they still read the same. Then an ammeter was removed and the voltmeter was hooked up to both ends. The voltmeter read 3 volts, the sum of the battery's charges, and the ammeter now read a current of 0 amperes. This was the case as the circuit was now open, meaning that electrical current is now not flowing throughout the circuit. Next, I measured potential differences for different segments of the circuit as labeled in the diagram shown. The voltmeter's measurements can be seen in the chart. A graph of potential versus position around the circuit was made, and by summing all the potential differences it showed that our model matched the theoretical prediction that the sum of the differences for a round trip of the circuit should be 0. In this section, it was important to note that when attaching the voltmeter to the circuit, the ammeter reading does not change as current does not flow through the voltmeter. For the next step in the lab, I then created a parallel circuit to the 100 ohm resistor with an ammeter and noted that the ammeter readings throughout the circuit became larger. This was caused by the nature of charge to flow through the path of least resistance. Then, using the potential difference measurements shown before and the equation given through Ohm's law, the resistance throughout segments of the circuit was calculated. I then created a resistor capacitor circuit with a 9 volt battery, 200 millifarad capacitor, and varied the resistance of a bulb. In the first figure you see the first step where the capacitor is charging. Throughout this process the light began bright and then slowly dimmed as the current in the circuit decreased. In the second figure you see the capacitor fully charged and see the buildup of opposite charges on the capacitor's sheets. Here the current read by the ammeter throughout the circuit was 0. The time measured for the circuit to reach this point using a 10 ohm and 20 ohm resistance bulb was measured and shown to be about 12.5 and 22 seconds respectively. The battery was then disconnected and the capacitor was connected directly to the bulb. In the first figure we see the capacitor discharging. The bulb began illuminated as the ammeter read a large current and then began to slowly dim again as the current decreased to 0. When the capacitor was fully discharged, as shown in the second figure, the ammeter again read that the circuit had 0 amperes of current, and now no net charge buildup was present in the capacitor. The time for this process was measured for a 10 ohm and 20 ohm resistance bulb to be about 11.3 and 19.2 seconds respectively. An RC circuit was set up similar to before, this time using a 9 volt battery, a 200 millifarad capacitor, and a 30 ohm bulb. The capacitor was charged and the battery was disconnected, and the capacitor was attached directly to the bulb and allowed to discharge. A voltmeter was attached to both ends of the capacitor to measure the potential difference at 21 second intervals. The initial voltage difference across the capacitor was 9 volts, the voltage of the battery. The natural log of the potential difference at a point of time divided by the initial voltage was calculated and plotted versus time, shown on the right. The line of best fit generated from this plot reflects the equation shown, where the slope of negative 0.1494 equals negative 1 over RC, leading us to obtain a computed RC value of 6.689 seconds. The theoretical one was calculated from Ohm's law in the equation shown and was obtained to be 6 seconds. The key findings of this lab were that we gained insight into some circuit components that we learned in class and obtained a computed RC value of 6.689 seconds to compare to a theoretical RC value of 6 seconds. This small difference was most likely caused by human error in stopping the timer at exactly 1 second intervals. To answer some theoretical questions, if instead the experiment was run using a real ammeter, the current read would be lower and the potential difference read across it using a voltmeter would be non-zero. This is the case as real ammeters, as opposed to the theoretical ones we used, have internal or intrinsic resistance, meaning they do affect the circuit. If an RC circuit was set up using a battery and capacitor with no resistor, our theoretical model would predict that the capacitor would reach full charge instantaneously, as the current would theoretically be infinite. Under real circumstances, though, this is not true, as there is some intrinsic resistance caused by the battery, so the charge time would be non-zero, as there is now resistance but still fast.